chose the topic Roscoe Wind Farm, where the first where we have to solve a lot of mathematical problems, and under the section there is the first assignment, which is we have to assume that the tower is a truncated cone, and thus we have to calculate the cross area section, the surface area, and the volume of the tower. And first of all, we have to find S, which is called the side length, and this is the formula for the equation. Sm square equals hn square plus the radius of the large end of the tower minus the radius of the top of the tower. And to do this, we have to put our own numbers in, where we have S equals h, which is here, and put it in square, plus a half O, which actually only is this introduction to cross-section area. The reason why we're doing the cross-section area is because when the wind is blowing at a high speed, we need to know how large we can make the cross-section area, because if it's too large, it might fall and get destroyed. And that's basically the idea behind the reason. Introduction to the surface area. We need to know the surface area because if we don't know it, we can't calculate or estimate how much sample painting we need to use, or how much material we need to use on the outside, and that is actually a problem.
We have to find the surface area of our truncated cone. Yeah, as you see here, we got a standard equation for that. The only difference is we have the big R is called radius of the bottom diameter, which in ours is just half an O. And the same thing for the small r's, the radius of the top diameter, but it's half a d, which basically gives itself. And the A surface now become this long sentence, which is basically this one, but with our specifications. And we got the result by plugging into the calculator of 80.13 pies. We used our Maple program to approximate it into a number, so we didn't have to read in pies, because pies is like different than we usually read. So we got this in meters. 251.73, 29, and 64. That's the space we got.
Introduction to volume of the tower. The reason why we want to know what the volume of the tower is because we want to know how much material we're going to use in the whole structure. And not only that, we also want to know how much space it's going to take.
And then we have to calculate the volume of the truncated cone. We use a standard volume for a truncated cone, and we just put in our measurements, just like we did before. Instead of a big R, we got half an O, and instead of a small r, we get half an d. Which makes the sensitive like this. We get the result of 185 i's, and we make our computer approximate it into this number, which gives us the result of 582.5690808 cubic meters. Yeah, not all day.
Yeah, now we got information that the tower we used in the first assignment wasn't the real tower. Now we have another tower which have the function of r h equals a lot of numbers, which is in our main documents too, and we said we wanted to find out the top diameter, so we set the h at 69. So we got the 1.25 zeros and 8.84, and it isn't really a lot different than the model tower. The radius is 1.25 and 7 zeros, 84 at the top radius, and the bottom radius at the ground is 2, and in the middle the numbers always change, of course, because it's a function, and it goes like this. And that's the reason why it's different, and we can't tell the radius in each place. So to find the cross area section, cross-section area, we have to use integration, and here we are doing the cross area section equals integration symbol 69 at the top and 0 at the bottom. So it goes from, so Mabel knows that we're going from 0 at the, so it goes from 0 and to 69 at the x, at x. We put the radius of the height in as a function and timed it with 2, because the tower doesn't look like this, it actually looks like this. At the end we got the result of 200 and 205.66, and more numbers, which is in our main document. Done. Introduction to the volume of the tower. The reason why we want to know what the volume of the tower is because we want to know how much material we're going to use in the whole structure. And not only that, we also want to know how much space it's going to take. Okay.
In the calculation of the real tower, we actually use integration again. We still have this basic function of our tower, which makes it look like this. And we still have a height of 69 and a beginning of 0, which makes our expression look like this. It's v real tower pi times, and then the integration. The bottom is 0 and the top is 69. The bottom is 0 because we only want the volume of the tower from the beginning point of 0, and we only want the volume to be top of the tower. That's why we have 0 and 69. When popping this into our calculator, we got a result of 156 and so on pi's, which we made our computer approximate into a number of meters, cubic meters, because that's what we measure volume in. And got the number of 492. Yeah, that was it. Introduction to why we calculate the area in the room. The reason for this being that if you are designing a real wind turbine, you have to have all the figures right. And when we just assumed that it was a truncated cone, we knew that it was
just straight, but that's not the optimal because then it will crack several places, and we will use a lot more materials. But if you have the wheel tower, we know that it is a curve, and thus the weight is distributed more evenly, and we actually can put it up. As a final part, we have to calculate the difference in loom of the wheel tower and the model tower. And to do this, we take the model tower and subtract the wheel tower from it, and thus we get the loom difference. And when we did this, we got 28 pi's, 28 times pi, and if we just approximate it to 10 numbers, we will get 90 and some decimal points cubic meters.